Next lecture on types of line patterns in fluid mechanics. This is very important when we try to represent a fluid which is flowing. How is it flowing inside a tube? So, we have to do a line representation. So, that is why this topic is very important, types of line patterns in fluid mechanics. In this lecture, we will try to see the introduction part of it, then what are the different lines, streamline, stream tubes, stream functions, then streak. Finally, we will try to see path lines and timelines. Very clear, path. How does a path move? A Brownian motion. So, that is called as path line. Timeline, how is the particle moving with respect to time? So, this is very important, because many a times what happens is people try to do flow visualization. When a fluid is flowing through a pipe, when it is flowing through a pipe, they would like to see how is the flow going. On the surface, if there are roughness, or on the surface if there are any undulation, how is the fluid responding? Because if the back pressure with whatever it gets generated because of the improper flow, then that can lead to burst in the tube. So, it is always important to understand and represent the fluid flow. In fluid mechanics is a highly visual subject. The pattern of flow can be visualized in a dozen different ways. There are many ways, but you have to represent a standard so that everybody can understand it. So, 4 basic types of line patterns are used for visualizing the flow, because the flow can happen like this, the flow can happen like this, the flow can go like this and come and then it can go like this, or the flow can go like this. So, these are different types of flow visualization. So, there are 4 basic types of line pattern are used to visualize flow. They are streamline, path line, streak line and timeline. Streamline is a line wherever tangent to the velocity vector at any given instant, you call it as a streamline. The path line is the actual path traversed by a given fluid particle. Streak line is the locus of particles that have earlier passed through a prescribed point is streak line. And timeline is a set of fluid particles to form a line at any given instant. So, these definitions are very important. Streamline is a line wherever tangent to the velocity vector at a given instant is drawn is a streamline. And streak line is a locus of a particle that have earlier passed through a prescribed point is a streak line. So, streamlines, any curve whose tangent in each of its point is at a given time collinear with the instantaneous flow velocity at this point, and that time is called as a streamline. A set of streamlines leaning at a given time on any closed contour is called as a stream tube. So, these are streamlines. Any curve whose tangent in each of its point is at a given time collinear with the instant flow velocity at this point, and that time is called as a streamline. A streamline leaning at a given point on any closed contour is called as a stream tube. From the given figure, you can see the streamline. This is a streamline. Okay. So, here is a tangent which is drawn. This is t equal to t1, streamline at time period equal to t1. Here it is t streamline time period is equal to T2. This is T1, you go like this is T1 and this is T2. So, here if you try to take a tangent, so it is velocity vector is V, which is m times L2, and when you see this one, it is m comma, it is not m times, it is m comma T2, it is m comma T1, the velocity vector is given like this. From the figure, we can note down that at the same fixed point of the flow field, the streamline represents curve varies over time unless the motion is stationary. So, it is there is a tangent which is taken. If the element arc length is dr of a streamline is to be parallel to V, their respective components must be proportional to dx by u, dy by v, dz by w, which is nothing but dr by v, where u, v, w are velocities. If the velocities u, v, w are known functions of position and time, the equation can be integrated to find the streamline passing through a initial point x naught, y naught, z naught with respect to time. In a free space, I am trying to take a point. This point with respect to time t. So, x, y, z and then time. The method is straightforward for steady flow, but may be laborious for unsteady flow. Unsteady means if there are lot of undulations or turbulence which is there, then this streamline diagram getting is very difficult. So, this method is straightforward for steady flows, but may be laborious for unsteady flow. Stream tube. Streamlines form a tube that is impermeable, since the wall of the tube are made out of streamlines, and there can be no flow normal to the streamlines. This tube is called as the stream tube. Streamline we studied here, this is streamline. The streamline form a tube, streamline form a tube. So, you see a tube. So, there are two circles. So, basically here is one and then you have all the streamlines going like this if you try to draw it in 2D. The streamline form a tube that is impermeable, since the wall of the tubes are made up of streamlines, and there can be no flow normal to the streamlines, then this tube is called a stream tube. Considering steady, I said here the method is straightforward for steady. Considering steady constant density flow over a cylinder, where the cylinder axis is normal to the direction of the incoming flow like shown in the figure. Consider steady state flow, constant density flow over a cylinder, right, over a cylinder, where the cylinder axis is normal, So, cylinder axis is normal to the direction of the incoming flow like shown in the figure. Far upstream of the cylinder, the flow is uniform in all the directions. We could call them as zero-dimensional flows. So, the flow near the cylinder, varies in the streamwise and normal direction, but not in the span-wise direction. You see here, there is a flow over a cylinder, there is a flow coming, you can see here as I told you, you see here about it. Then after this, over a period of time, then it gets streamlined. Span is what? This way. So, the flow near the cylinder is two-dimensional. In this region, the streamlines come closer together and the area between them decreases. closer together and the area decreases. Since the density is constant of the water whichever is flowing, the velocity must increase according to the principle of mass of conservation. Density of the fluid which is flowing is constant. The velocity increases according to the mass conservation. For a constant density flow, wherever the area between the streamline decreases, the velocity increases. These two are very important. You should understand the density is constant, so the velocity must increase according to law of conservation of mass. For a constant density flow, whenever the area between the streamline decreases, the velocity increases. This is what we infer out of this streamline. So, the stream function, from the figure we can compute the volume flow dq through an element. We take a small element ds of controlled surface of unit depth. So, dq is equal to, we try to define as a function d phi by dx into dx plus d phi by dy into dy is equal to delta phi. Okay. So, here you can see the element which is here. So, that the displacement in x, y, and here is ds, and this has a velocity vector v equal to iu plus jv, right. So, this is the velocity vector for this. So, if you extend it n, which is n is equal to dy by ds I minus dx by dsj. So, you get this point. So, this point can be represented as q, volume flow q, which is nothing but velocity vector times n multiplied by dA, which is nothing but d phi. So, this is what we have said here. We have pictorially represented. This is the control surface. This is a control surface, unit depth into the paper. So, it is into the paper. So, this is the geometric interpretation of the stream function. So, we can compute the volume flow dq from stream functions. A stream function also exists in a variety of other physical situations when only two coordinates are needed to define the flow. We use the stream function. The steady plane compressible flow, the density is variable. So, here what we saw, density is constant. So, here what we are seeing, the density is variable, compressible flow, but that W is equal to 0. So, the representation in an xy plane is given by the continuity equation dou by dou x rho u plus dou by dou y rho v equal to 0. So, this is for a steady plane compressible flow. Therefore, a compressible flow stream function can be defined in this way. So, you are just trying to rearrange. Density rho u is nothing but dou phi by dou y into rho v is equal to minus is important, dou phi by dou x. The line of constant psi are streamline of the flow, but the change in psi is now equal to the mass flow, not the volume flow. So, the d m dot mass flow can be found out by rho v times n into dA. This rho v times n comes from here. V times n dA is equal to dou phi. So, through this we can try to find out the compressible flow stream function, and the line of constant psi are streamline when it is in flow. Next, let us move to streak lines. A streak line is the locus of a particle. Locus is locus of a particle that had earlier passed through a prescribed point is called as the streak line. So, you can see here, this is the point which is there, and when the line which passes through it, The line which passes through it is called as a path line. Streak lines are produced by continuous release of marked particles such as dye, smoke and bubble. So, streak lines are used basically for flow visualization. Streak lines are produced by the continuous release of marked particles, right, from a given point. If the flow is steady, the streak lines will be identical to the streamlines if the flow is steady. But in reality, never it is. So, the streak line will be identical to streamline and the path line of the flow. By integrating equations with the condition that a particle whose streak line is related to a point MO, which is XO, YO, ZO, is located at a point t equal to tau, we obtain the following equations. X, Y, Z is nothing but x is x naught, y naught, z naught, t, and t is the time and tau. So, x naught, y naught, z naught, t and tau is located at a point at t equal to tau. Thus, when t is fixed, the tau varies. When t is fixed, time is fixed at a fixed time, tau varies and over an integral 0 to infinity. Tau varies between 0 to infinity. The previous equation of those streak lines related to the point m naught is at a point t. So, this is very important. On the other hand, for a fixed tau, when t is fixed, there can be only two conditions: t fixed, time varies. When time is fixed, tau varies. On the other hand, when tau is fixed and t varies, these same equation identify with those of the particle's trajectory, which at a time t is located in the starting point of m naught of a streak line. Friends, this itself is a big topic, but in basics we just would like to cover through this. So, you have to understand stream line, then stream tube, then stream function, 3 points. Then you will try to know about streak lines and then its equation. Streak lines as shown in the figure, this is a figure, in the figure, and as a direct consequences of the definition, the streak line is a time varying curve composed of different particles. You can see here at t equal to 0, 1, 2, 3, 4, 5, 6, 7 at the trajectory, you can see at varying time intervals, right. This is the trajectory of the particle is this, right, when t equal to 0, 1, 2, 3, 4, 5, 6 it is going. So, here you can see the trajectory of the particle is this when t equal to this much. So, and then when the trajectory of the particle is this, t equal to 1, 2, 3, 4, 5 you get. So, streak lines related to point A will be this line, this will be the line, right, for a point t. Particle, this is trajectory A, this is trajectory triangle, trajectory circle and hexagon. The streak line as a curve related to a given point can be generalized as a streak surface and a streak volume. This is line. When several of these lines come like this, it forms a surface. When I try to do it inside a tube, it is like this. So, it is a volume. By considering at a time t the set of particles which have all passed through the same lines or same surface representatively at any earlier time is called as a streak line. So, I go back and redefine it. A streak line is a locus of a particle that have earlier passed through a prescribed point, locus of a particle. So, streak lines are this. Path lines. Path line is the actual path traversed by a given fluid is the path line. So, streak lines is you take a locus and then you try to draw of a particle. Path line is exactly what it has travelled. Path line is the actual path traversed by a given fluid particle. Streamlines, path lines, streak lines are identical in a steady flow. The path line is a curved parameterized in time which refers to the same particle. Okay. So, this is the same particle m1, m2. These are the velocity vectors at given m1 and m2 time t1 and t2. So, this is the path line and this is a different time. A path line is a line traced out by a given particle as it flows from one point to another. So, this is here one point to another. This is the line which is traced. It is almost to your CAD what we do, right? Control of the, you try to the starting point, ending point, and then you will have control points. So, something like that. The path line is Lagrangian concept that can be produced in the laboratory by marking a fluid particle and taking a time exposure photograph of the motion. So, what we do is you try to have a particle and then you try to, with respect to time, you have a high speed camera and then you keep on be seeing where is the particle moving. The last part is timeline. A timeline is a set of fluid particles that form a line at any given instant. A timeline is instantaneous line, while the path line, the timeline is an instantaneous line, while the path line and streak line are generated by the passage of time. Instantaneous is time. Experimentally, a timeline can be generated by a single discharge of marked particles through a wire. You give a sudden surge, there is a spark, the electrodes are fixed here, sudden you pass a very high current, there is a spark which happens. With that spark, you try to take a photo. Experimentally, a timeline can be generated by a single discharge of marked particles from a wire. The velocity profile shown in the figure is really a timeline generated earlier by a single discharge of bubble from the wire. So, you can see here there is a discharge and then you can see how does it happen. The velocity profile is made visible by a line of hydrogen bubble discharge from the wire across the flow. So, here there is a flow which happens and here there is a wire which is kept. Right. So, this is what we talk about timelines. To recapture in this lecture, we saw what are streamline flows, we saw what is a path line, streak line, and then we also saw what are the state of timelines and the importance in fluid mechanics. Then we saw what are stream functions, state, and we have explained to it. These are the references which we have used and thank you very much.